Welcome back to the deep dive. Now, this session is critical. We're not doing a general survey today.
No, not at all.
We are doing a highly focused, very high-stakes examination review, and it's specifically tailored for you for the Gujarat University MD Anesthesiology written and Viva exams.
And we're targeting what is probably the single most consistent 20-mark question you're going to face.
Anaesthetic breathing systems.
Exactly. We're talking about that crucial interface between the machine and the patients. So the circle system, the Bain circuit, and the entire Mapleson family, A through F. This topic is it's non-negotiable for safe practice.
It really is.
Now, before we dive in, we do need a brief word of caution. It's about the preparation materials you sent over to us for this review.
Yes. Our role here is to pull out the highest yield nuggets from the source material you share with us. But after a pretty critical review of your notes for this particular section, we found a massive, and I have to say, a pretty unacceptable gap.
It's a big one.
The comprehensive details you absolutely need to score highly on a 20-mark question here. The components, the schematics, the specific Mapleson classifications, and those critical fresh gas flow requirements, they are entirely missing from the notes we received.
And as senior faculty guiding your exam prep, we can't just shrug and move on. This topic is mandatory. So we're making an executive decision here.
Okay.
We're going to proceed not by trying to extract nuggets that aren't there, but by delivering the high-yield MD-level content that examiners absolutely expect you to know by heart.
So this deep dive, this transcript, this is now your roadmap.
This is it. This is the detailed information you must internalize immediately. Our mission is to make sure your structure for answering this question is impeccable, and we're going to turn what could be a 0-mark potential into a 20-mark success.
All right, let's do it. Let's start with the absolute basics. When that question begins, describe anesthetic breathing systems. What is the fundamental definition, the purpose we need to articulate to get those first few marks on the board?
Okay, so a breathing system is the assembly of components that connects the patient's airway. So usually via a mask, an LMA, or a tracheal tube, to the anesthetic machine or the ventilator.
It's the conduit.
It's the conduit for gas exchange. And its core purpose is really twofold. First, it's about the precise delivery of the anesthetic and oxygen mixture, the fresh gas flow, or FGF, to the patient.
Right.
It has to maintain the required partial pressure of the volatile agent. Second, and this is just as important, it has to efficiently manage the patient's expired gases, ensuring the safe, reliable elimination of carbon dioxide, while maybe allowing for some partial rebreathing.
That clarity is absolutely essential. But why does this specific topic carry such a heavy weight? Why is it so reliably worth 20 marks in a high-stakes MD exam?
Because it represents that immediate physical interface where, engineering and pharmacology meet human physiology. It's as simple as that. If you fail to understand the breathing system, you fundamentally fail to deliver safe anesthesia.
It's a direct reflection of your clinical competence.
Completely. Understanding the systems, their resistance, their efficiency, the volume of rebreathing, their specific hazards, it's mandatory for safe and also cost-effective practice. Mistakes here, like running insufficient FGF in a Mapleson circuit or having an incompetent unidirectional valve in a circle system, they lead to immediate life-threatening hypercapnia and hypoxia. Okay. So mastery of the component function, the physics behind it, and the flow rates you need, that's the single best demonstration of your clinical readiness.
So it's a critical thinking test wrapped inside an anatomy question.
A very good way to put it.
Given that, how do examiners usually structure these long-form, high-mark questions? What should you be ready for?
You've got to prepare for two main question archetypes. The first is a highly detailed description of the most complex modern system. So, describe the classification, components, working, advantages, disadvantages, and clinical uses of the circle system. That requires really deep mechanistic knowledge.
And the second type?
The second archetype is comparative. It tests your grasp of flow dynamics and efficiency. So something like compare and contrast Mapleson A and Mapleson D systems, justifying their differing fresh gas flow requirements during spontaneous and controlled ventilation.
And they might add a little extra on top.
They often do, like state how the Bain circuit modifies the Mapleson D principle. So you need pre-prepared structures for both of those, and we are now going to provide the detailed information you need for both types of answers.
All right, let's get into it. The first segment of any high-scoring answer has to be a clear, concise classification. This shows the examiner you've structured your thinking logically from the get-go. How should you structure this initial categorization?
You start with the most fundamental operational characteristic. How does it get rid of K-co-Euro? The primary division is based on the presence or absence of a co-Euro absorber. That is the functional split that really drives the economics and the complexity of the whole system.
Okay, so let's break that down. Systems without an absorber.
Right, so systems without an absorber, which you can think of as non-rebreathing systems,
Yeah.
these rely completely on high fresh gas flow, or FGF, to physically flush the expired carbon dioxide out of the system before the patient takes their next breath.
And this category includes?
This includes all the Mapleson systems A, B, C, D, E, F, and modified versions like the Bain circuit. But, and this is a key point, they are non-rebreathing circuits only if the FGF meets or exceeds that necessary washout flow.
And the other side of the coin, systems with an absorber.
Exactly. These are the rebreathing systems, and really we're talking about the circle system. It uses a chemical absorbent, soda lime or bear lime, to remove CO chemically. This allows a patient to rebreathe the expensive volatile agent, which also helps conserve heat and humidity.
That distinction, that fork in the road, it directly leads to the second crucial layer of classification, right? Rebreathing versus non-rebreathing.
Yes, and this is paramount because it dictates the second vital clinical factor you have to manage, the fresh gas flow requirements.
So for the non-rebreathing systems?
For the non-rebreathing high-flow Mapleson systems, to prevent rebreathing of Ruiuros, your flows have to be high. We're talking 1 to 3 times the patient's minute ventilation, or MV. This is, resource intensive and it's costly.
Whereas for rebreathing systems, like the circle,
It's the opposite. It's a low flow system. Since the Tiuro is being removed chemically, you can get away with low flow or even minimal flow anesthesia. Your flows only need to replace the patient's oxygen consumption and the amount of volatile agent being taken up by the body.
and then there's that third layer, the traditional categories, which honestly can sometimes be the most difficult to define clearly. Open, semi-closed, and closed systems. Why do examiners still insist on this terminology?
They persist because these terms describe the degree of rebreathing and how waste gas is managed, which links directly to safety and cost. So you really have to master this.
Okay, walk us through it.
Right. So open systems are pretty much historical, like simple insufflation. No bag, no rebreathing, very little containment. Semi-open systems have minimal or no rebreathing, and some ambient air might even be drawn in. Think Mapleson E or Mapleson A or D when your flow is just extremely high.
And semi-closed, that's where most modern practice sits, isn't it?
It is. Semi-closed means partial rebreathing happens, and the excess gas is vented out to the atmosphere or a scavenger through a valve. This is the definition of a standard modern circle system at typical flows, say 1 to 2 liters per minute. It's also how the Mapleson systems operate when the flow isn't quite high enough to prevent all rebreathing.
Which leaves closed systems.
Right. Total rebreathing. Here you only replace the oxygen being consumed and the APL valve stays closed. This is the most efficient, but also the most demanding mode, and it's only achievable with the circle system.
Okay, so now we can fulfill that exam requirement. Place the circle system, the Bain circuit, and all the Maplesons within this classification.
And a high-scoring answer provides a table for this, or at least structures it this way. So Mapleson A through F are primarily classified as non-rebreathing systems. Clinically, they operate as semi-open or semi-closed, depending on your flow rate relative to the minute ventilation. And they all lack a co-Euro absorber.
And the Bain.
The Bain circuit is functionally a modified Mapleson D, so it's also non-rebreathing and typically operates as semi-open or semi-closed.
And finally, the circle system.
The circle system is a rebreathing system. Clinically, you'll operate it as semi-closed most of the time with some venting. Less commonly, you might run it as a truly closed system with minimal flow and no venting.
That structural framework is perfect. It secures those initial marks. Now let's move to the system that gets asked about the most, the circle system.
The big one.
The circle system is often that standalone 20-mark question. We need to detail every aspect of its design and function. Let's start with the components. What are the 6 non-negotiable parts you have to describe and be prepared to draw accurately?
Okay, the structure is complex, and it's complex for a reason. It has to ensure unidirectional flow through the absorber. So number 1, the inspiratory and expiratory limbs. These are just the large bore corrugated tubes connecting the patient to the apparatus.
And the corrugations are there to reduce kinking, and the large diameter reduces resistance.
Precisely. Number 2, the unidirectional valves. These are the defining safety components. There's one in the inspiratory limb and one in the expiratory limb. They prevent any backflow of gas. Their function is absolute. They force the expired gas to go through the KEO absorber.
So an exam answer has to stress that valve competency is essential.
It's everything. A sticking or incompetent valve will let gas bypass the absorber, and that leads to hypercapnia no matter what your fresh gas flow is.
Got it. What's component number 3?
Number 3 is the Q-absorber itself. This canister contains the chemical agent, usually soda lime, which is a mix of calcium hydroxide, water, and a little bit of sodium or potassium hydroxide.
And you need to know the reaction.
Yeah, you absolutely do. The reaction is exothermic, which means it produces heat and moisture.
Hey.
That's a huge advantage because it helps conserve the patient's body temperature and airway humidity. You should know the basic chemical reaction. Co-Euros plus water gives you carbonic acid, which then reacts with the calcium hydroxide to form calcium carbonate and more water.
And there's an indicator dye in there as well?
Yes, usually ethyl violet, which changes color typically from white to purple when the granules are exhausted and the pH drops.
Okay, number 4.
Number 4, the reservoir bag. This acts as a compliant storage volume. It accommodates the demands of breathing in and out, and crucially, it lets the anesthetist manually assist or control ventilation.
Number 5.
The adjustable pressure limiting valve, or APL valve. This is your exhaust valve. It vents excess gas, the volume of FGF that isn't being consumed, into the scavenging system. It stops excessive pressure from building up in the circuit, and its location is very important, usually on the expiratory limb.
And finally, number 6.
The fresh gas inlet, or FGI. This is just where the mixed gases from the anesthetic machine enter the system. In a well-designed circle, the FGI should enter the circuit just before the inspiratory valve to make sure fresh gas doesn't bypass the patient.
That level of detail, both chemical and mechanical, is exactly what's needed to secure full marks. So let's pivot to function. How should you describe the working of the system during spontaneous ventilation?
Right, so during spontaneous breathing, the patient initiates inspiration. They draw gas from the inspiratory limb, which has already passed through the absorber. The APL valve is set partially or fully open.
So on inspiration?
On inspiration, the patient draws gas in. The inspiratory valve opens, the expiratory valve closes. Simple. On expiration, the patient exhales co-Euro gas. Now the inspiratory valve closes and the expiratory valve opens. The gas goes into the expiratory limb, moves through the Q-Euro absorber where the Q is stripped out, and then that clean gas fills the reservoir bag.
And what about managing the pressure?
Since FGF is continuously entering the system, the APL valve just lets that steady excess volume escape. This keeps the circuit pressure low while making sure all the expired gas is routed through the absorber before the next breath is taken.
And how does that change fundamentally when we switch to controlled ventilation?
The change is all about the APL valve and the pressure dynamics. When the anesthetist is controlling ventilation, either manually with the bag or mechanically with the ventilator,
The dynamic shifts completely.
it does. On inspiration, the anesthetist compresses the reservoir bag, or the ventilator drives the breath. Now, to deliver that positive pressure, the APL valve has to be closed or switched to ventilator mode. The gas is then forced through the inspiratory limb, and that inflates the lungs.
And expiration.
During expiration, the pressure drops. The lungs passively deflate, pushing gas through the expiratory limb and into the absorber. The key distinction here is that the pressure generating the tidal volume is controlled externally, and the APL valve's function shifts from managing continuous flow to managing peak pressure and venting during the expiratory phase.
This inherent complexity gives rise to the system's specific advantages and disadvantages. What are they?
The advantages are heavily weighted toward efficiency and physiology. First, conservation of heat and humidity. Because the gas is rebreathed and the absorption reaction is exothermic, it delivers warm, humid gas. This reduces mucosal damage and body heat loss, which is a huge clinical benefit, especially in long cases.
And the economic benefit.
Economy. It conserves expensive volatile agents because you only have to replace what's metabolically consumed. You can run low FGF. That also means reduced pollution, less waste gas vented into the OR, and it provides a very stable inspired gas concentration once you reach equilibrium.
And the disadvantages. They seem to center on complexity and safety.
They do. It's bulky, it's heavy, and it has numerous components valves, an absorber that can fail. The large internal volume means changes in anesthetic depth, so wash in and wash out, are slower than in a low-volume Mapleson system. And the biggest one is the safety risk. The consequences of component failure, like an exhausted absorbent or stuck valves, are immediate and potentially catastrophic hypercapnia. That's a major point for examiners.
So in terms of clinical uses, where is the Circle system the preferred system, and why is that?
It is the standard workhorse for modern, prolonged adult anesthesia. It's preferred whenever you want to do low-flow or minimal-flow anesthesia for economic or environmental reasons.
Right.
Also, whenever heat and humidity conservation is critical, so long surgeries, burn patients, neonates, elderly patients, and of course, whenever controlled ventilation is required over a long period.
Now let's address the danger. Common faults and their clinical consequences. What are the high-yield Viva traps here?
Okay, beyond the obvious, like running out of your volatile agent, examiners will focus on component failures that lead to co-uro retention. Number one being exhausted co-uro absorbent. If the absorbent is depleted, the co-uro is not removed. You'll see a progressive rise in inspired co-uro and subsequent hypercapnia. The clinical sign is a rising EDCO on your monitor and physical signs of hypercarbia tachycardia, sweating, bounding pulses.
And the second, more acute failure.
An incompetent unidirectional valve that's stuck open. This is lethal. Gas just flows back and forth between the patient and the reservoir bag, completely bypassing the absorber. The co-uro level builds up incredibly fast. The clinical consequence is acute, severe respiratory acidosis and hypercapnia.
How do you spot that?
You have to visually check the dome of the valves. They should flutter or move, confirming they're working. If they're not moving, that's a massive red flag.
Any other common faults?
Misplaced FGI or APL valve.
Yeah.
If the FGI is introduced between the patient and the inspiratory valve, fresh gas can be forced back down the expiratory limb, disrupting the one-way flow.
Yeah.
Or if the EPL valve is placed incorrectly, it can lead to rebreathing.
All right, let's shift gears. We're moving from the complex low-flow circle system to the simpler high-flow Mapleson circuits. These are defined purely by physics and arrangement. What is the general concept of the Mapleson classification?
The Mapleson systems are characterized by their extreme simplicity. They rely on gas dynamics, not chemical absorption. The classification, standardized by Mapleson, uses the physical arrangement of just 3 key components relative to the patient connection to define the system's efficiency. The systems are A, B, C, D, E, and F.
And the factors affecting that efficiency are purely the positions of those components. The fresh gas inlet, the reservoir bag, and the APL valve. How does their position dictate performance?
Efficiency hinges entirely on the system's ability to use that continuous fresh gas flow to act as a sort of a piston or a flush to expel the co-uro-rich exhaled gas before the patient takes their next breath.
So if co-uro remains in the tubing near the patient, it gets rebreathed.
Exactly. The arrangement determines how effective that co-uro washout mechanism is, and that changes dramatically between spontaneous and controlled ventilation.
Let's systematically go through each system, A through F, paying really close attention to those crucial flow requirements. Those are mandatory for the exam. Let's start with Mapleson A.
Right, the Magill system. This is the historical archetype. The arrangement is key. The FGI is near the bag at the machine end, and the APL valve is located close to the patient connection.
And its main advantage is in spontaneous ventilation.
Its supreme advantage. It is the most efficient system for spontaneous breathing. The FGF enters and fills the long reservoir tubing. When the patient exhales, the co-uro-rich gas pushes the fresh gas ahead of it towards the APL valve, which is right there by the patient, ensure the co-uro is expelled first.
So the fresh gas flow requirements are low?
Very low. FGF is approximately equal to the patient's minute ventilation to prevent rebreathing. So FGF is about 1 times MV.
But it's extremely inefficient for controlled ventilation.
Terribly inefficient. When you squeeze the bag, the positive pressure pushes the fresh gas that's near the bag out of the APL valve near the patient. The co-rich gas near the patient just stays in the reservoir tubing, waiting to be rebreathed.
So the FGF requirement for controlled is very high.
Very high. You need 2 to 3 times the minute ventilation. Its clinical use is primarily historical or for short, spontaneous breathing cases. Its inefficiency during control really limits its general utility today.
So the exam mantra has to be A for spontaneous, D for controlled.
Nail that down, and you've got the core concept.
What about Mapleson B and C?
B and C are often seen as sort of theoretical steps in the evolution towards D, though C does have some historical clinical relevance. For both of them, the FGI and the APL valve are positioned very close to the patient. C is just like B, but with a very short expiratory limb.
And efficiency.
They're notoriously inefficient in both spontaneous and controlled ventilation. Because the FGF and APL are both right by the patient, the exhaled gas just gets mixed back into the inspiratory volume. You get inevitable rebreathing unless your flow is exceptionally high.
How high?
2 to 3 times MV is typically required. Mapleson C can be used for controlled ventilation for short periods, but its main utility is really historical or just theoretical for the classification.
Okay, so let's get to Mapleson D. This is the next essential system after A, and it represents the flip in efficiency.
Correct. The Mapleson D arrangement is optimized for controlled ventilation. The arrangement is the FGI is close to the patient, and the bag and APL valve are remote at the far end of a long expiratory tubing.
Which makes it highly efficient for controlled ventilation.
Very efficient. When you squeeze the bag, The positive pressure pushes the expired gas down the long tubing towards the remote APL valve. The continuous FGF at the patient end acts as that piston we talked about, efficiently pushing the exhaled Kiro out.
And the FGF requirements for that?
Efficient. FGF is about 1 to 2 times the Menite ventilation. It's less efficient than Mapleson A for spontaneous breathing, though. It requires a higher flow, maybe 1.5 to 2 times MV, because that long tubing allows for more mixing and co-pooling.
So it's extremely common.
Extremely common, especially in its modified coaxial form, which is the Bain circuit. It's ideal for controlled ventilation and for transport or remote locations because it has so few components.
Which brings us to Mapleson E and F. These are critical for the pediatric discussion, and they link back to those physiological concerns about low resistance.
Yes, Mapleson E and F are really the gold standard for small patients. They address that physiological imperative of minimizing resistance to breathing.
Let's start with E, Ayres T-piece.
Mapleson E's is the simplest form. The arrangement is just a T-piece. You have an FGI on one arm, the patient connection on the other. It has no reservoir bag and no APL valve. The third limb is the expiratory limb, which is just open to the air.
So resistance is minimal.
The lowest possible, virtually. The flow path is extremely short, there are no valves, but it relies entirely on a high FGF, 2 to 3 times MV, to continuously flush that open expiratory limb.
And the Mapleson F, the Jackson-Rees modification.
The arrangement is a Mapleson E with a crucial addition. A reservoir bag with a small escape hole, or a little APL valve at its tail.
So it keeps the low resistance but adds control.
Exactly. It retains the low resistance of the E, but the bag allows the anesthetist to assist or control ventilation, which is absolutely vital for neonates and infants. So E and F are preferred for pediatric anesthesia, especially in neonates and infants and also in MRI, and really any time resistance must be absolutely minimal.
Okay, the Bain circuit. It's a variation of the Mapleson D, but it really warrants its own discussion because it's so popular and has those unique safety risks. A perfect Viva topic.
It really is. The Bain circuit is essentially the Mapleson D principle, just re-engineered for convenience and portability. And its core feature is its construction and coaxial design.
Explain the coaxial design and why that's a benefit.
Coaxial just means along the same axis. The fresh gas is delivered through a narrow, flexible inner tube, while the exhaled gases return via the wide outer tube that surrounds it. The patient connector is where that inner tube terminates, which effectively places the FGI right at the patient's airway, the critical arrangement for Mapleson D efficiency.
And this design has a couple of main advantages.
It does. First, the physical separation means the outer tube can be quite long without being too bulky. Second, the working principle uses thermal exchange. As the cool, fresh gas travels inward, it's passively warmed and humidified by the warm exhaled gas flowing outward through the outer tube.
So it conserves some heat and moisture.
It does, which makes it superior to a standard Mapleson D in that respect.
And the fresh gas flow requirements are therefore identical to the Mapleson D.
Exactly. 1 to 2 times MV for controlled ventilation. But, and this is the big debate, while the design is convenient, it carries a unique and potentially lethal hazard that examiners love to test you on.
Let's focus on that. The hazard specific to the Bain circuit. What is the absolute worst case scenario?
The primary hazard is the disconnection or kinking or tearing of the inner fresh gas delivery tube. And because that inner tube is hidden within the outer sheath, failure is silent and you can't see it.
So if the inner tube disconnects?
If the inner tube disconnects near the machine end, the fresh gas is just dumped into the outer sheath, far from the patient. The patient then inhales gas from that outer tube, which is now almost pure dead space, filled with high concentrations of their own expired Kio.
The co-flushing mechanism is gone.
Completely gone. This results in immediate, massive, and rapidly progressive hypercapnia. Kinking is another one. It completely obstructs fresh gas delivery. The patient struggles against extreme resistance if they're breathing on their own, or the bag becomes impossible to squeeze.
This high-stakes hazard demands mandatory pre-use checks. What are the specific tests to detect inner tube disconnection that an MD student absolutely has to be able to describe with the Viva?
2 tests are mandatory for the exam. They test the integrity of that inner tube. Number 1 is Pethick's test or the Venturi test.
How does that work?
The procedure is you occlude the patient end of the outer tube. You close the APL valve. Then you flush the inner tube with a high flow of oxygen, say 5 to 10 liters per minute.
And the expected result if the tube is intact.
The high flow through that narrow inner tube creates a subatmospheric pressure in the outer tube because of the Venturi effect. This negative pressure actually causes the reservoir bag to collapse slightly.
And if it fails? if the tube is disconnected.
If the inner tube is disconnected, the fresh gas flows directly into the outer tube, pressurizing it and inflating the reservoir bag. It will not collapse. That confirms the life-threatening disconnection.
What's the second test?
The occlusion test, or compression test. You occlude the patient end of the circuit, close the APL valve, and pressurize the bag. It should hold pressure. Then when you quickly release the occlusion at the patient end, you should feel a vigorous blast of gas escaping, confirming flow through the whole circuit. If it's kinked, the bag will be impossible to squeeze.
So focusing on its utility, what are the primary clinical situations where the Bain is preferred?
Because it's lightweight, flexible, and has long tubing, it's highly suitable for remote location anesthesia. So think head and neck surgery, ENT, ophthalmology, where the patient's head is draped and the anesthetist needs to be positioned away from the surgical field.
And for transport.
Excellent for transport. Moving a ventilated patient over short distances is much easier with a Bain than a full circle system.
Okay, we've established the deep detail required for each system. Now we have to synthesize this into those high-scoring comparison and exam tables. What are the critical comparisons you need to be ready to deploy?
3 comparisons are essential because they highlight the fundamental trade-offs in anesthesia. So Circle versus Mapleson systems, Mapleson A versus D, and Bain versus Circle.
Let's start with Circle versus the Maplesons in general.
Right. The contrast here is between complexity and efficiency versus simplicity and high flow. So for coaxial removal, Circle uses chemical absorption. Maplesons use a gas flush. For rebreathing, Circle allows it. Maplesons try to prevent it with high flow.
FGF requirement is low for Circle, high for Mapleson.
Exactly. Heat and humidity is conserved in the Circle, but poorly conserved in the Maplesons. Resistance is high in the Circle because of the valves and absorber, but low in the Maplesons, especially E and F.
Wash in and wash out is slow for Circle, rapid for Mapleson.
And portability is core for the Circle. It's bulky and excellent for the Maplesons.
Okay, next comparison. Mapleson A versus D. This is the most common conceptual trap, and the answer has to focus strictly on the mode of ventilation.
Precisely. This tests whether you understand how the arrangement dictates the gas physics. So, FGF position. Remote in A, near the patient in D, APL position. Near the patient in A, remote in D.
Efficiency and spontaneous breathing. Best for A, inefficient for D.
And the opposite for controlled ventilation. Worst for A, best for D. And you should be able to explain the mechanism. For spontaneous in A, exhaled KO euros flush directly out the nearby APL. For controlled in D, the FGF acts as a piston, pushing Coro out the remote APL.
Perfect. And the final comparison. Bain versus Circle. This contrasts the two modern standards.
Here, the emphasis is on convenience versus conservation. The Bain is a coaxial, low-volume design. The Circle is a unidirectional flow, high-volume design. The Bain is not suitable for low-flow anesthesia. The Circle is highly suitable.
Safety check for Bain is Pethick's test. For Circle, it's valve competency and the absorbent status.
Right. Resistance is low to moderate in the Bain, but high in the Circle. Suitability for long cases. Less so for the Bain due to poor heat and humidity, but excellent for the Circle. And finally, cost. The Bain is cheaper to buy, but expensive to run because of the high gas flows. The Circle is expensive to purchase, but cheap to run.
Excellent. You have to internalize those 6 points per comparison. They are the definition of high-yield content.
They really are.
So we must now shift to the clinical rationale. The examiner wants to see that you can select the correct system based on the patient and the procedure.
Exactly. This is where you apply the knowledge.
So in terms of choice of breathing system for spontaneous ventilation, we know Mapleson A is theoretically the most efficient. Is that what's actually used clinically?
Theoretically, yes. Mapleson A gives you the best economy. But in practice, it's actually quite inconvenient to connect to a modern scavenging system. So clinically, if spontaneous breathing is preferred, practitioners often just use the Circle system at modest flows, maybe 2 to 4 liters per minute, because it simplifies equipment and gives you those heat and humidity benefits.
And for quick procedures?
For quick procedure, a standard Mapleson D can also be used. You just accept the slightly higher flow requirement.
Conversely, for controlled ventilation,
Mapleson D, or the Bain circuit, is preferred when simplicity and efficiency during control are paramount. So, short to medium length procedures, or where you need portability. The Circle system is the absolute standard for controlled ventilation in all long cases, especially when you want to use low-flow techniques.
let's talk about pediatric anesthesia. Our general source material stresses the physiological vulnerabilities of neonates' respiratory mechanics, high metabolic rate. Why is the choice of systems so critical here?
In small children, the ratio of the equipment's dead space to their own tidal volume is critically high. Any resistance you add to the circuit massively increases their work of breathing, and that can lead to rapid exhaustion, fatigue, and hypoventilation. So the physiological imperative is simple: lowest resistance possible.
Which is why Mapleson E and F are preferred.
It's exactly why. The E to F systems have minimal components and no unidirectional valves, unlike the Circle. This drastically reduces the frictional resistance to flow, which is crucial for neonates and infants. The Mapleson F allows you to assist or control ventilation while maintaining that minimal resistance.
And the Mapleson E and F systems are also favored in high-stakes neonate cases, like the repair of congenital diaphragmatic hernia, CDH, which is a critical procedure in the wider exam syllabus.
Absolutely. In a CDH repair, the goal is often protective, minimal ventilation, and really tight control over the PACO. We know from physiology that hypercarbia and acidosis are major triggers for pulmonary hypertensive crises in these fragile infants.
Right.
So a low-resistance system that lets you make rapid manual adjustments, like the Mapleson F, is essential to prevent those sudden co-euro spikes or pressure changes that could compromise their pulmonary vasculature.
What about where simplicity and speed dictate the choice, like in short procedures?
For very brief, simple procedures, especially those involving an inhalation induction, the Mapleson D or Bain is often chosen. They have a shorter time constant than the Circle system, which allows for rapid wash-in and wash-out of the volatile agent. It just speeds up the transition to and from anesthesia.
And finally, transport and emergency settings.
Portability is king. Any system used outside the main OR needs to be light, durable, and simple. The Mapleson D or Bain circuit wins here, hands down. They don't need an absorber canister, they're easily coiled, and they're often used in pre-hospital care, MRI suites, or during complex intra-hospital transfers.
Okay, let's talk diagrams. A clearly labeled diagram is not optional. It's mandatory for a passing score on a 20-mark question. If you skip the diagrams, you're confirming a conceptual weakness. We have to address the 4 diagrams that are essential.
Absolutely. Let's start with the most complex one, the Circle system. The diagram has to clearly illustrate the circular, unidirectional nature of the flow. You have to draw the Y piece connected to the patient.
The 2 long limbs.
The 2 limbs and the unidirectional valves correctly positioned. One on the inspiratory, one on the expiratory limb. And make sure you draw them with a clear one-way mechanism, like a little flap. Then the co-euro absorber canister, the reservoir bag, the APL valve, and the fresh gas inlet location. All 6 components.
For the Mapleson circuits, the diagram's power is in demonstrating that component arrangement. Which specific arrangements should be memorized?
Mapleson A, the Magill arrangement, and Mapleson D, the standard arrangement, are non-negotiable. For Mapleson A, you draw the long corrugated tube, place the FGI near the machine or bag end, and put the APL valve proximal, close to the patient connector. This visualizes the washout mechanism for spontaneous breathing.
And for Mapleson D?
You draw the long tube again, but this time you place the FGI right next to the patient connection, and you put the APL valve remote near the bag end. This visualizes that piston effect for controlled ventilation.
And the final mandatory diagram, the Bain circuit.
This one has to show the internal structure. You draw the outer corrugated tube and then clearly draw the thinner inner tube running coaxially. You have to label the inner tube as fresh gas delivery and the outer tube as the exhaled gas return space. This proves you understand the safety risk associated with those 2 independent flow paths.
And what are the key labeling points to secure maximum marks across all these diagrams?
3 things. 1, direction of gas flow. Use arrows consistently. 2, APL valve location. Correctly label and locate it, as this is the primary determinant of Mapleson efficiency. And 3, QO removal site. Explicitly label the QO absorber in the Circle system, and for the Maplesons, label the APL valve as the primary QO expulsion site.
Okay, this section is all about turning conceptual weaknesses into clinical mastery. Let's talk common mistakes and Viva traps. What are the most common misconceptions about fresh gas flows?
The most widespread conceptual error is confusing the Mapleson A and D efficiencies. Students see the Mapleson D or Bain used with a ventilator, and they just assume A is irrelevant or less important. You have to understand that the FGF requirements are not interchangeable.
So misstating the flow requirements is a huge red flag.
A massive one. Saying you need low flow for Mapleson A during controlled ventilation or for Mapleson D during spontaneous ventilation, it just reveals a fundamental misunderstanding of the gas dynamics. Secondly, students often confuse theoretical minimum flow with clinical practice flow. Clinically, we almost always run higher flows than the theoretical minimum to increase our safety margin and responsiveness.
Let's focus intensely on the typical Viva questions and safe answers. If a patient suddenly becomes hypercapnic because of a breathing system failure, what is the full physiological cascade the examiner is looking for in your answer?
They're testing your ability to connect equipment failure to systemic consequences. So you start with the initial problem, acute Guerrero retention. For example, a Bain inner tube disconnect or a circle valve failure.
And the immediate consequences.
The immediate consequence is a rapid onset of respiratory acidosis, increased PACO, decreased pH. Then you talk about the systemic effects. Cardiovascular. Guerrero causes powerful cerebral vasodilation, which increases cerebral blood flow. This can dramatically increase intracranial pressure, ICP, especially in neurosurgical patients.
It also triggers a sympathetic response.
Exactly. Tachycardia, hypertension, which can be detrimental in patients with coronary artery disease. And severe acidosis is a known trigger for pulmonary hypertensive crises in vulnerable populations, like the neonates with CDH we discussed.
And the clinical signs you'd see?
A sudden rise on your ETICO monitor, increasing resistance when you're bagging, and nonspecific signs like flushing or an increased heart rate.
That detailed answer linking the failed valve to respiratory acidosis, increased ICP, and pulmonary hypertension, that demonstrates an MD-level grasp of the material. What about that classic Bain trap?
The examiner will ask, if the inner tube of the Bain circuit disconnects, what do you see and how do you confirm it? The safe answer sequence is 1. Clinical observation, sudden, massive increase in ETICO, possibly resistance to manual bagging.
2. Confirmation.
Immediately perform Pethick's test. If the bag inflates or stays distended during the high flow and occlusion, the tube is disconnected. And 3. Immediate action. Disconnect the Bain, switch to a simple T-piece or a manual resuscitation bag with high oxygen flow, and immediately replace the entire Bain circuit. You do not waste time trying to fix it.
One final Viva trap. How do you check for exhausted soda lime?
You check the color indicator, the ethyl violet changing from white to purple. But the clinical answer is more important. If the CO Euros level starts creeping up despite adequate ventilation and flows, you must assume the absorbent is exhausted and replace the canister immediately, regardless of the color. The color change can sometimes be unreliable.
Okay. We've covered extensive ground, providing the detailed content that was missing from your prep notes. Let's synthesize this into a high-yield bullet point recap for rapid exam revision.
Right. First, the Mapleson classification is based purely on the component arrangement FGI, bag, APL, relative to the patient. Second, efficiency is diametrically opposed. Mapleson A is best for spontaneous, D and Bain are best for controlled.
The circle system allows for economical low-flow anesthesia and excels at heat and humidity conservation through chemical co-Euros absorption.
And the circle system is fundamentally dependent on the competency of its unidirectional valves.
The Bain circuit, though convenient as a Mapleson D, carries that unique lethal risk of inner tube failure, which mandates the use of Pethick's test before you use it.
In pediatric circuits, Mapleson E and F must prioritize extremely low resistance to minimize the infant's work of breathing. Finally, all circuit failures leading to co-Euro retention cause immediate respiratory acidosis, demanding rapid intervention to prevent severe systemic consequences like high ICP or cardiac instability.
And what are the 10 to 12 take-home exam points you absolutely must prioritize memorizing? The numbers and concepts that will secure the marks?
Okay, here we go. 1. Know the 6 components of the circle system and the function of each part. 2. FGF requirements. Mapleson A is 1 times MV for spontaneous. Mapleson D Bain is 1 to 2 times MV for controlled. Commit those numbers to memory.
3. Draw and label. Be ready to draw the circle, Mapleson A, D, and the Bain coaxial design clearly.
4. Efficiency rationale. Be prepared to explain why A is poor for control because it wastes fresh gas, and why D is good for control, that piston effect. 5. Pethick's test. Be able to describe the procedure and interpret the result.
6. Low resistance systems. Justify using Mapleson EF in neonates by discussing the risk of increased work of breathing.
7. Circle faults. Detail the consequences of incompetent unidirectional valves. 8. Acid-base connection. Link hypercapnia from a malfunction to the immediate onset of respiratory acidosis. 9. Clinical use case. Know that circles for long cases and low flow, and Bain or Mapleson D is for remote locations and transport.
And to conclude your 20-mark essay, you need a strong summary paragraph.
You do. Here is a model conclusion you could adapt. The choice of a breathing system in modern anesthetic practice is a deliberate clinical decision founded upon an exhaustive understanding of gas physics, flow dynamics, and patient safety. While the Mapleson classification provides simple, portable solutions often favored for short procedures in pediatrics, particularly Mapleson E and F for low resistance, the circle system remains the standard for prolonged adult anesthesia due to its economic and physiological advantages of low flow capability and superior conservation of heat and humidity. Mastery of the underlying principles, specifically the arrangement of components, the corresponding fresh gas flow requirements, and the critical safety tests of systems like the Bain circuit, is non-negotiable, representing the foundational knowledge required for safe and effective practice in the MD anesthesiology examination.
That provides the comprehensive high-yield structure and content you need. You have the necessary roadmap. Now, you need to go immediately populate your study materials with these diagrams and detailed mechanism descriptions.
Indeed. Get those notes up to standard. You have been given the answer key. Now you must internalize it.
And as always, we'll close with a final thought to mull over, something extending beyond the immediate exam context. We emphasize the necessity of low resistance in the Mapleson E and F systems for neonates, linking it to the low compliance and high metabolic demands of the infant airway.
So consider this. The resistance to flow is a factor of both laminar and turbulent flow dynamics. We know that sharp bends, kinks, and changes in diameter increase resistance, and they specifically favor turbulent flow, which increases the pressure drop exponentially.
Okay.
So what are the specific geometric differences between, say, a shortened Mapleson C circuit, which has bends and restrictive valves, and the Mapleson E and F circuits? How does the Mapleson F arrangement, specifically the large diameter, short tubing, and the elimination of flow-restricting unidirectional valves, how does that minimize the factors that generate turbulence, making it such a physiologically elegant solution for ensuring minimal work of breathing in a critically ill infant?
So think about the internal geometry and the flow patterns.
That is the true physics behind the clinical decision.
Food for thought and for deep understanding. Thank you for joining us for this high-speed, high-stakes deep dive into your exam preparation. Good luck.